Number 1, metal block, 80 degrees. Listen, please. Shh. Metal block, 80 degrees, in a room that's 20 degrees, is placed in water with a temp 18. Explain the energy transfer. There's 2 things that are happening here. So if you just talked about one, that's not enough. Olivia, go ahead.
The energy will transfer out of the block into the air and the water because the block is warmer than them.
Very good. Perfect answer. It's converted from transferred from the block to the water and from the block to the air. That's the part some students might miss. So I know I talked to you too and I left that part out. I want you to discuss that on your own. So anyways, yeah, the concept there, energy always moves from high to low, high concentration to low concentration, or another way to say that, energy moves from
high to low.
Besides that, warmer to colder, or hot to cold, higher temperature to lower temperature, all of those things. Remember that for tomorrow, okay? Remember that for tomorrow. What about number 2? Who thinks they can explain that to the class? What's the mass of Cl2?
No.
Okay. It is 10 grams. Very good. How'd you figure that out? 15 minus 5, but explain for everyone to understand. Part of it, and then you'll get the rest of it. What's that law? What is that showing? Go ahead.
That energy can't be, or mass can't be created or destroyed, only transferred.
Good. What's that called?
Conservation of mass.
Conservation of mass, right.
Oh, yeah,
So
yeah.
if you have 5 grams of this and 15.0 grams of that, think of the arrow as like the middle of scales, right? So I think Willow said this, like the scales of justice. Yeah. So you have the scales want to be balanced, right? So your reactants and your products should have the same weight or mass. So again, this is kind of like the equal sign. 5 plus 10 equals 15. So 15 is balanced with 15. That's conservation of mass. Tomorrow there's a couple questions about that, right? That's why I'm reviewing it with you. 3, how can NaCl AQ be separated? So that's, what do we call that in like normal life? Salt water. Okay, that's salt water. NaCl AQ is just a symbol for it. So who can tell me, how do we separate salt water? Kieran?
Evaporation.
Good, evaporate the water. Is that a physical process or chemical? Physical, you're just evaporating, so it's still water and it's still salt. That's a physical process. What type of mixture is this? Homogeneous, right. Homogeneous, homogeneous, good. If I was to put sand in there, that would make it heterogeneous, right. All right, and what if sand was in there? Then we could do this other process to separate it. Filter, right. You can't filter salt water, it just goes right through, but sand would stay on top. Good, you guys seem like you're ready here for tomorrow. What about water? How do we separate water? If we boil the water, we still have water, it's just steam. So when I say separate, I mean let's take the H and the O apart. So, but good try. I mentioned it, but how about just an overall concept? Could any physical change separate the water?
No.
If we freeze, boil, melt, condense, sublime water,
No.
it's still water, right? You're not separating the water, you're not breaking up the H and the O. So what do we have to do to it? Something, someone just said. Chemical change, good. Yeah, so the answer here could just be a chemical change. You don't have to give me a specific answer. The real answer is called electrolysis, and that is running electricity through water. So the reason I'm bringing this up now is you need to remember compounds like water can only be separated with chemical changes. So remember that. They're put together chemically, they're separated chemically, okay? But yeah, if you run electricity through water, you'll get hydrogen gas and oxygen gas. I have a contraption called the Hoffman apparatus. I haven't really looked at it yet. I've never used it myself. But once I can figure it out, I'll show you guys at some point this year. You hook it up, run electricity through the water, and you have these 2 containers, 2 test tubes. One of them has hydrogen, one of them has oxygen. And one of them has twice as much gas. Which one would that be?
Hydrogen.
Hydrogen, because it's H2O, right. So it actually literally works. You can see it. It's cool. So I'll show you that. All right. So that's good review. Let's go to the homework now. All right, so where are we? 45. Oh, you know what? Let's refer to our notes. So take our notes out. We're going to kind of look at those graphs. What? Mocker, go get it quick. Take out those graphs from yesterday. Trevor, do you like to hike?
Sometimes.
All right, good.
I like hiking more than Trevor.
We'll use you as an example later. It's more fun that way.
I like hiking more than Trevor.
No, you don't. You don't.
Hiking on the what?
I like hiking more than Trevor.
No, he doesn't.
Use me as
No, use me.
Maybe I can use both of you.
No.
Yeah.
no.
All right, 45. Heating a contained gas that is held at a constant volume increases its pressure. Why? Okay, remember yesterday I was trying to use the plants as an example, and it really went south on me there. So the concept there is,
You weren't here.
I'm not going to go into it again. It was basically, if you want to do an experiment and there's multiple variables involved, you always need to hold at least one variable constant so you know that one isn't changing the outcome.
Yeah.
So, right, but the analogy I guess didn't work so well. So if we have the graph temperature versus pressure here, pressure versus temperature, what do we have to hold constant? What do we write down? Volume. So there's three factors that affect gases: pressure, volume, and temperature. So if I sealed, let's say I had some neon gas inside here, okay? We sealed it up. All right, so let's say this was airtight.
Yep.
This would be constant volume, right? Because this is a certain size, it's rigid. No matter how much we heat this up or cool it down, the container isn't going to change size. So that's what this means at constant volume. So if we were to heat this up, so the question says, heating a contained gas that is held at constant volume increases its pressure. We know this. Temperature goes up, pressure goes up. So in here, if there was a gas and we heated this up, eventually what might happen? Yeah, it would burst, right? Because the pressure gets too high. Someone tell me why. Answer this question. Raise your hands, please. Why? Why does the pressure go up?
Because they're colliding.
Yes. Raise your hand.
Because they're colliding.
Yes, they're colliding
Particles of gas.
more frequently or less frequently?
Oh, a lot.
Right. So I did this morning. It's a really simple example here. But if a gas that's really cold kind of does this, right? Just collides once in a while. What would I do if it gets hot?
Go a lot faster.
Right. Go a lot faster. Okay. So it's a very simple example, but that's the concept. So in here, particles are hitting each other slowly. If you heat it up, particles are flying around, smashing into each other more often and harder, more force. That's why that works. All right. But we have to hold volume constant to keep that graph intact, right? You can't graph three variables there. We're only graphing two. 46. What happens when a gas is compressed? Raise your hands. So that would be actually this graph here, sort of. Let's say we cool it down. Or we look at this one. This might be actually a better one. Forget that. This one. If we add a lot of pressure, right? So we're increasing this pressure. We're compressing it. Raise your hands. What happens to the volume according to this graph right here? Nick, decreases. So the answer to the question is gas particles take up less space. So the gas particles get closer together. When you compress a gas, they take up less space. The volume will shrink. What's the analogy I use with that? With the temperature and volume. If we decrease the temperature, what's the analogy I use? I want you to really think about this.
Plants.
No, not plants.
Most of vegan.
The sponge, or what was the other analogy I used? If these animals get cold, penguins, they huddle together. So, same concept. If you compress a gas, that's the sponge, compress it, it takes up less space. And if you cool it down, it takes up less space. Same thing, they huddle together. All right, so I say these things, I show you stuff to try and get you to understand it, because again, I really don't believe memorizing is the way to go. You memorize it, that's not learning anything. You just memorize it. All right, 48. If you compress the gas from 4 liters to 1 liter, what happens to the pressure? So if we take a container, this makes me think of Star Wars too.
I haven't done the picture
Sweet. Here's 4 liters, here 1 liter, right? Gas takes up a certain amount of space in here. If we transfer all this gas into this container, will the gas particles have more or less space in here? Less space. Okay. So Autumn, you're our collision expert here. Pretty sure that's the title of somebody at like a auto body shop. But anyways, so if there's a certain number of collisions in here creating a certain amount of pressure, and then we transfer all this gas in here, so they're going to be more cramped, would you expect more or less collisions? More, because there's less room. So who can finish this? Answer the question of 48. What happens to the pressure? It goes up. That's this. If you decrease the volume, right, decrease the volume, you're going to have a high pressure. So pressure increases for number 48. Pressure increases by how much? By what factor? Close. 4.
How do you know that?
It's an inverse relationship. So if your volume went down by a factor of 4, 4 divided by 4 is 1. So your volume went down by a factor of 4, your pressure goes up by the exact same amount. So it went up by a factor of 4. That's called the gas law, and we'll talk more about that. Well, we won't talk. I will tell you on Monday in the video.
Well, how did you know that that was 4 times the size of that?
It told you. It says it.
Oh,
It says 4 liters to 1 liter.
So I didn't read this thing yet.
Yeah, but it's right here. 4 to 1. 4 to 1.
Oh, that looks like a UL and an IL.
Okay, Karen, just stop on it.
49. Why is Kelvin specified? Because Kelvin is directly proportional to kinetic energy. I'd be surprised if anybody got that. Good job, Trevor. Good job. That's a hard question, okay? When I first read it, I was like, what are they getting at? Kelvin temperature is directly related to kinetic energy. That's why we use Kelvin, not Celsius. All right, 50. All right, Caitlin, take a balloon from this room. Put it in the freezer. Leave it in there for a few hours. Take it out. How's it going to look? Same or different? So you literally blow up a balloon. It's this big. Yay big. Put it in the freezer. Leave it in there overnight. Take it out in the morning. You think it'll be yay big? Or yay big? Or yay big?
Yay big.
Smaller. Very good. Yes. So the answer to the question 50 is the volume of the balloon decreases. Andrew, why? So the balloon in this room is pretty warm. It's 24 degrees Celsius. That's pretty hot. 70 something. Let's see. 70, almost 76 degrees in here. So if we go outside and it's like, maybe not today, maybe it's 10 degrees out in the wintertime, why would the balloon shrink? What do gas particles do when they get cold? They condense, right? Down here. Animals here. Animals, right? The penguins. Animals. Penguins. Penguins. Penguins do that. Penguins condense. Okay? Same thing. It condenses when it gets cold. All right. 55. Oh, Kieran, this is appropriate for your brother.
Okay.
Why do aerosol containers display the warning, do not incinerate?
Because they're flammable.
And?
Don't blow up.
Very good. They'll blow up. So let's say this is an aerosol can of aerosol, whatever, however you say that. Right? Aerosols. Who even has aerosols anymore? Anybody?
Isn't that like air freshener?
I guess an air freshener, yeah. Okay. So if you throw this on a bonfire, it will explode eventually because what builds up? Pressure. Right, you get that. Good. Moving on. And Autumn, why does the pressure build?
They're colliding.
Very good. More collisions. Very good. All right, 76. What it says what real gas, but I told you yesterday 2 on the chart.
76? We just went from
76.
55 to 76.
Oh, did we not do, oh, I'm sorry. 59. Sorry, 59. Explain why it is impossible for an ideal gas to exist. That's, well, who has an answer? Amanda, sounds good. Because real gases actually take up space and have volume, and there's one more thing. Ideal gases claim to not have any forces of attraction. I'm just going to answer this, sorry. So that's impossible. Every single thing in this world that you interact with, even the air, has forces of attraction. They're weak, because they're gases, they're weak, but they have them. So ideal gases can't exist because they claim they don't have forces, and that's impossible. That's why they don't exist. 60, describe an ideal gas. The way I want you to think of an ideal gas is a gas that just keeps expanding until it doesn't exist. So if I said to you guys, act like an ideal gas, what would you do?
Walk in the opposite
Right.
direction.
Everybody would walk opposite direction for hundreds of miles till you're just literally by yourself.
Well, until actually.
Okay, so just think expand. Okay. 61. How come real gases deviate? What's deviate mean? Willow, what's deviate mean?
I don't know.
I think you do. I bet you do.
But I do.
Yeah. So like, if you were on your cell phone right now, and I said, Willow, please put your phone away, and you said no, you would be deviating from what?
Opposite.
From what? You would be if you were on your phone, I said, please put it away, and you flat out said, no, I'm not going to.
I'd be
Deviating from what?
what you said.
From the rules, right? Yeah. So she'd be deviating from the rules. Okay. So what's deviate mean? Go against. Very good. So go ahead, Amber. You're an expert on this one. Real gases. I don't know why I said that. No reason. Yeah. Why real gases deviate from ideal? What do you got for that one? If you need a little help, I can help. Good. So real gases have volume. Great answer. Yes. Very good. There's another part to that, though. I want to add one. Adriana, what do you think? Real gases also have these. So gases are far apart, but not to the point where they don't exist. They kind of near, they're sort of near each other-ish. Yes, real gases actually have forces of attraction. Good. All right, now on the back. 76. Okay, go ahead. Yes, very good. And that is because of forces of attraction. Yeah, in AP chemistry.